In this video, we're going to attempt to demonstrate graphically what's happening with the symmetries in calculating the a sub k's and b sub k's. So for example, we have an odd function f of t, which is this blue square wave. You can see that it's constructed as an odd function. Now, in calculating the b sub k's, we multiply f of t, this square wave, by the sine waves of frequencies that are integer multiples of the fundamental frequency. For an odd function, we've pointed out that, and we want to now try and demonstrate, that the b sub k's will not be 0, but the a sub k's will be 0 for an odd function. So, looking first here again, for k equals 1, the frequency of the sine wave will be the same as the frequency or the fundamental frequency of our periodic waveform. You'll notice that the positive lobe, negative lobe of f of t coincides with the positive lobe of the sine and the negative lobe. So when k equals 1, and it turns out for any k value, you get this type of alignment where you get 1 or 3 waveforms or 5 cycles within this same period, but we can see what's happening easiest if we limit ourselves to just the k equals 1 term. So what's happening here? B sub k is the integral of f of t, the square wave, times the sine. So there's f of t times the sine. This is positive when this is positive, it's negative when this is negative, and so you have a positive times a positive that gives you a positive lobe. A negative times a negative gives you a positive lobe. And when you then integrate over that product, you get a net area. Thus, the b sub k's are not equal to 0 in an odd function. Now, what's happening for the a sub k's in this odd function? Well, a sub k is calculated by taking the odd function and multiplying it by cosine. The cosine function is an even function. It's effectively the sine wave shifted 90 degrees to the left. So here's what we've got. During this positive lobe, you have a positive part of the cosine wave and a negative part of the cosine wave. So that when you multiply this times this, you get a positive times a positive during this part, but a positive times a negative during that part. So you get a positive area here and a negative area here during the first half. Similar situation during the second half. And when you integrate that up, there's as much area of positive as there is negative area, and the a sub k's are 0 for all values of k in an odd function. There are no cosine terms in the Fourier expansion of an odd function. Now, this f of t that we're looking at is also half-wave symmetrical. So let's now look and see what it is about the half-wave symmetry that makes it so that even the b sub k's are 0 for even harmonics, or for values of k being even numbers 2, 4, 6, and so on. We have here the situation of a sine wave oscillating at 2 times the frequency, or k equals 2 omega naught, 2 times the frequency of our half-wave symmetrical function. And hopefully you can see here that in this we're going to get a complete cycle, and you get a complete sinusoidal cycle in the first half and a complete sinusoidal cycle during the second half. And because it's half-wave symmetrical, the second half is the negative of the first half. And again, when you do the multiplication, you get positive times positive is a positive lobe. Negative times positive is a negative lobe, similarly on the second half. And when you have an integer number of cycles, integer number of sine wave cycles in a period, say it right, an even number, not just an integer number, but an even number of cycles, 1, 2 is an even, the areas above, or the positive areas of the product, are equal to the negative areas of the product, and when you integrate across to that, the b sub k's or the areas cancel, and so when k is 2, 4, or 6, the b sub k's will be 0 also. And we've already demonstrated that the a sub k's are equal to 0 for all values of k when f of t is odd. You can see what's happening here. During the positive lobe, you've got one complete waveform. During the negative half, the second half of the half wave periodic function, you've got another complete waveform. The product of this times this is that. The product of this times this is a positive lobe, and then you get positive times negative gives us a negative. It turns out that this area here plus this area there is the same as that area there, so that when you integrate, again, the a sub k's equals 0. So we have then, when there's half wave symmetry, the b sub k's, the sign terms where you have an even number of periods in one period of your function, those b sub k terms will be 0.